All right, so we're going to take a look at lesson 23, which is about antiderivatives. So far we have spent a lot of time on derivatives. We've looked at how to take them, and we've looked at their applications. So now we're going to ask a question that kind of turns the process around, which is, if we're given a function f, how do we find a function whose derivative is that function f? So it's kind of the first of several lessons, all of the rest of this class actually, which will be kind of focused on this process. So I'm going to start by asking this question, or a couple of questions, I guess. So I want to write down a function whose derivative is f of x equals cosine x, or write a function whose derivative is f of x equals 3x squared. Or the last one, write a function whose derivative is x to the fourth. So we all should be able to come up with, at least one function. I'm going to call them capital F of x. So what about sine x? The derivative of sine x is cosine x. So that function would answer the first question. What about the second question? I want the derivative to be 3x squared, so certainly an x cubed would give me that, but I could make it slightly more interesting by maybe adding 4 to it. So then the derivative of capital F of x is still 3x squared. And last but not least, okay, if I want a function whose derivative is x to the fourth, I know it's going to need to be an x to the fifth power, but because of that, if I took a derivative of just x to the fifth, I'd have 5x to the fifth. I need to put it over 5 so that the 5s would cancel in the derivative process. And again, I could add some sort of constant to it if I wanted to. It still isn't going to change the derivative of that function. So would we be doing this in class? I would ask you to look at somebody else's and compare. You could compare to what I wrote. Were your answers the same? And could you come up with different answers? Or is there only one answer to all of these questions? And so I kind of spelled that out as I was doing my second and third examples here, where actually there's infinite possibilities, because I chose to add 4 and 400e, but I could have added any constant whatsoever, and it still wouldn't have changed the derivative of the function. So the answer is no, there are infinite. No to is there only one answer. That there are infinite possibilities. And really the key there is that you could add any constant, since the derivative of the constant is 0, then it's not going to change your derivative. So it gives you a lot of options. So we're going to have a name for these things, and these functions are called antiderivatives. So a function, capital F of x, is called an antiderivative of little f of x if capital F prime of x is little f prime for all x. So it's just a word to describe a function whose derivative is this given function. And in the next page, I've kind of drawn, or I haven't drawn them, I guess I've graphed them and made them pretty colors, a family of functions. So if we had looked at that first example, we were asking about, write a derivative, a function whose derivative is cosine. Well, in fact, you have an entire, these are not all of them, but here's a whole series of functions that's derivative is cosine. So the red one in the middle, I think here, right? This one is our typical just plain old sine x. It's centered on the x-axis, right? It goes up one, down one. But then what's happened, and I've just drawn a few of them, from the red one to the green one, and then the green one to the blue one, the blue one to the black one. Each one of these is just same exact shape, period, everything. It's just gone up one unit, or from yellow to red to yellow down. So I could write equations for all of these. This would be y equals sine x plus 1 or sine x plus 2. You get the idea. And this is, of course, not every single answer, because we would be here all day if we tried to write every single one of them out. But it's just a few of them, a handful of the functions that are in that family of antiderivatives of f of x equals cosine x. Okay. And as we noted on the last page, the difference between all of these is really just the constant, right? That's being either added or subtracted. Oops, I guess I should try to make that somewhat grammatically correct, being added or subtracted. And we do, in fact, have a theorem which should make for pretty logical sense that tells us if you have an antiderivative, you've got your capital F, and it's an antiderivative of little f on some interval, then the most general antiderivative, like the way we could write it most generally, is that capital F of x plus c. And we call c an arbitrary constant. So we just put that there as like a placeholder for, and you could add anything that's a constant to this function. So this is what we would call the general antiderivative of f. So we can use that to actually find or write down some general antiderivatives for functions. And again, we're just kind of asking ourselves, what function has a derivative that's equal to the given function? So what function has a derivative that's equal to sine? It's not cosine, because its derivative would be negative sine. So we need a negative cosine. That negative times the negative sign will give us the positive sign derivative. But then if it's the most general, I need to add a plus c. So it just holds the place for that arbitrary constant. C could be any constant. Okay, so what about number 2? What function has a derivative that is 1 over x? And you probably just said ln of x, and you are correct. So we can write ln of x plus c. However, we just got to point something out here. What is the domain of this g of x function? 1 over x. What can I plug into that? Anything except for 0, right? But what about ln of x? What can I plug into that function? That's anything bigger than 0. I can plug negatives into little g of x here, but I cannot plug negatives in to this f of x antiderivative that we found. So when we do the antiderivative of 1 over x, we add absolute values to the x inside the ln. And the reason for that, okay, we add absolute values. So the domain match. The domain of the ln matches the domain of the derivative, the 1 over x. So they're both defined everywhere except for 0. Okay. All right, moving on to a few more examples. So kind of number 3 is asking us to come up with a formula. If I have, oh, I don't know why there are 2 equal signs there. N does not equal 1. So anything except for, oh, it's supposed to be a negative. That's why. That's supposed to just be -1. Because if n is -1, then I would have x to the -1, which is 1 over x. We just did that. That one doesn't act like all the others. Okay. But if we were to look at other ones, so let's look at an example. X squared, I think we just did x to the 5th. Well, let's try x cubed. Okay, so if I'm starting with x squared and I want to rewrite a function that has the derivative that is x squared, I know I have to go up 1 in the power. Then what happens, as we said when we did the 5th, is that if I take a derivative of x cubed, that 3 would pop out front. And since there's no 3 here, then in order to compensate for that, I'm going to put the 3 down there. So that now when I take the derivative of this function here, it'd be 3x squared on top, and it would be multiplied by 1/3, and the 3's would cancel. Same thing goes for x to the 3rd. I need it to be an x to the 4th. So when I take its derivative, it goes down to x to the 3rd, but I need to put it over 4 to cancel out the 4 that will be the coefficient of the derivative. So do you see a pattern here? If I start with n, what's happening? It looks like my power is going up by 1, which makes sense because I'm going the opposite direction of the derivative. But then I'm also dividing by that same number. And so this is going to actually end up being a formula we'll use to do antiderivatives of x raised to a power. Just like we had the derivative of x to a power was this formula. Remember that? Seems like so long ago. But now we have a way to go in reverse, essentially. Okay, looking at just a couple more. Number 4 and number 5. There's a very good way to tell if you remember your derivatives of inverse trig functions. Because if you do, you know what these are. And if you don't, then you don't know what these are. This one is inverse tan. And this one is inverse sine or arcsine, arctan, either way. So antiderivatives of things that were just formulas, pretty straightforward. What function gives us a derivative of 6e to the x? 6e to the x. So e to the x is its own derivative, and therefore it's its own antiderivative. And for something where we're adding together two terms, we can go ahead and apply. Make that a little smaller so I can see my rule up here. We can go ahead and apply this rule and just do it term by term like we did before. So x to the 3rd, I'm going to add 1 to the power and divide by that same number. Keep the 12 in front of my next term. Add 1 to the power. Divide by that number. So it looks like I have x to the 4th over 4 plus 2x to the 6th. Oh, don't forget my plus c. The directions did ask us to do the most general form of the antiderivative. So that's always going to have your plus c. And then last but not least, number 8 says find g of x if g prime of x equals this function. So it's still just finding an antiderivative. It's just phrased slightly differently, where they wrote the function they gave you as g prime of x. So if you look at this function, I mean, I can't come up with on the top of my head a function whose derivative is that, right? But what can I do since there's only one x in the denominator? I can simplify this g prime of x, I'll leave the 4 cosine x alone, but then I'm going to write that as 2x to the 5th over x, which is 2x to the 4th, minus square root of x over x, which is x to the negative 1/2. So now that I've rewritten it, I should be able to go back through term by term, looking at what gives me a derivative of cosine. That would be sine. I will add 1 to the power and then divide by that number. Add 1 to the power. If my power is negative 1/2 and I add 1, I'll get 1/2. Adding by 1/2 is the same thing as multiplying by 2. Okay. A lot you can do with that. I mean, you could write the square root, I'm sorry, the x to the 1/2 as a square root of x. I'm not sure that does you a whole lot of good, but it's certainly an option.